All right. How you guys doing? Sorry, I'm running a tiny bit late here. The internet's always a little sluggish, so I think we're good. So please sign in if you haven't, and we'll get going. So last time we were working on sedimentation. We solved a problem at the end of class, kind of taking a look at how quickly particles will settle, and made a comparison between some velocity parameter that we solved for the particle to some velocity we could define as the slowest velocity that a reactor could settle. So last time we left off there. Today I want to take a look at how do we improve settling velocity as a treatment in order to make better use of gravity, let particles stick together, and then fall faster, essentially. That way, again, the theme here is if we can make it cheap and reliable and remove some contamination, we're going to do it. And it turns out removing particles is great because they can hide some pathogens, they can contain some metals or things maybe we don't want to consume. And so if we can just get rid of particles using gravity, perfect. That's a good thing. Okay, so we will talk today about flocculation, coagulation and flocculation. So, a coagulant is a fancy word for something that kind of works like a glue to allow particles to stick together and to coagulate. You probably have heard of aggregation. It's another good term here. The coagulant will cause particles to aggregate, and we're going to use that term interchangeably. Flocculation would then be that process of aggregation and allowing aggregation to occur. So we will talk today a little bit about what makes a coagulant work, why does it work, what are the underlying physics and chemistry that allows it to work, and then get into how do we design a mass balance to understand how quickly it's going to work in a flocculation chamber. Yeah. Both coagulation and flocculation are that process. The reason this is a little confusing is because you can call it coagulation. Coagulation is, if you look at the word co, together, agulation, some particles coming together. So yes, but we call it a coagulant that's causing that to happen. It's two terms that in practice we call it a coagulant and then we send it through flocculation, but we could say it's a flocculant and send it through coagulation. So just bear in mind that these terms mean almost the same thing. They're used specifically to typically say we are going to cause coagulation and then allow time for flocculation. Don't worry too much about it. The terms are very similar. A floc, F-L-O-C, is a small particle that is comprised of smaller particles. So this is just a small aggregate. Okay, almost like a flock of birds, except more like a flock of turds. Okay, sorry. Now, and that would be for wastewater. All right, so coagulant dosing, this is just a quick process. You send it through, you inject some chemical or some salt. We'll talk about that. Rapidly mix it so it disperses, and then you give it time for particles to meet. That's our flocculation, is how we're going to describe it. But again, it's a good point. They kind of both mean the same thing. So we talked about sedimentation. So really what I meant is here is after the first sedimentation, we get to coagulation dosing. So we've talked about primary sedimentation. Next we go into a rapidly mixed small chamber, just boom, inject our stuff, and then send it to a larger chamber where flocculation is given some time to occur. All right, so let's talk a little bit about particles and what size can we remove without coagulation, just as it is, And then what maybe can we remove once we do this enhancement, causing them to stick together? So if we think of a scale, a size scale, where we have particle size here on the x-axis in micrometers, we can go up to 1,000 micrometers here. That would be 1 millimeter, right? So that's getting to the point where you can see it visibly. Might be a little bit difficult to see. You might have to look pretty close to see the each hole in the screens in our screen porch or in the shades in the back here. But once you get close enough, you can probably see it with your eye, naked eye, right? You don't need a microscope or anything like that. So this range here kind of describes that. All the things visible, maybe even down to 10 or so micrometers. Now, I think that probably it's a little, I think we'd have a hard time seeing anything this small. So that would include the size of human hairs, stuff like that, rain, mist. Once we're getting to the size of pollen and fog, it becomes very difficult to see an individual grain of pollen. Maybe some crazy large, weird plants might produce pollen large enough where you can see an individual one. But at some point, we're going to need a magnification. So that's kind of giving us some scope of where we are in terms of what you've seen or experienced in real life here. So once we get down to around 10 micrometers, if you remember our example was dealing with particles around that size, 10 or 20, maybe a little larger, we started having some difficulty removing them. Now, of course, the particle density matters too, so it's not just the size, but we already talked about the particle diameter being very important for the settling velocity. So the larger the diameter, the faster it's going to settle. So once we're in kind of this range, we're getting to the point where we probably need to assist the process and cause the particles to flocculate. Now, if we take a look at some of the more pathogenic type of things that we might care about, we'll see we have what are called Giardia and Cryptosporidium cysts. These are pathogens that are single-celled organisms, but the large kind. So they're not quite bacteria. They're still, if you remember from biology, these are eukaryotic. A lot of times you might call them a parasite, a single-celled parasite. A parasite is an organism that kind of preys on some other organism, taking over some part of it, just parasitizing it. It can be a larger organism, but these would be single-celled parasites. These tend to be a little larger. They have a thicker cell wall. They can make these little cysts that are pretty resistant to chlorine and some other treatments. So can we get rid of them with gravity? Well, probably not until we cause them to stick to some other particles. So they're in that range where we probably don't expect to remove them, but we're close. Bacteria would be in this range where some of them are smaller than 1 micron. Some of them are several microns. There's actually some really weird exceptional cases where you can see a single bacteria with your visible eye out at like 50 microns or 100 microns. So kind of neat. I don't think there's any pathogens that size, but there exists a few bacteria that big. You have algae here. Some algae cells would be large. Eventually we're talking about cyanobacteria, so technically bacteria, but probably lumped into this. And then we've got viruses. Not a chance, right? So unless a virus is going to stick to some other particle and be removed that way, they're making it through, right? Gravity is going to do nothing for them. At some point, they're small enough where simple diffusion will keep them suspended. They're never going to meaningfully settle at all, right? So viruses are quite small, tend to be something like 50 nanometers. So if we go down to 0.0001, we'd end up with 1 nanometer, whereas this is 10 nanometers and 100 nanometers. So if you consider nanoparticles, that's kind of generally what we're talking about as anything here or below. You'll see nanofiltration, things like that. So that would be the realm that we're talking about. Okay, so that's just a bit of an overview of what we can expect. We'll also take a look at the same thing again. I'll remind you about this when we talk about filtration. what can we remove with a given membrane, what size of stuff can we expect, and how much pressure will be required. But for gravity, we can expect not a lot of the really concerning stuff, the pathogens, but maybe we can get some of them if we cause them to stick together to other particles. So how do we do that? What drives particles together and what drives them apart, right? We could almost think of this as a relationship, a lesson on relationships and how to come together or how to stay apart, right? But for particles. So particles, there's a couple different forces involved. The first would be electrostatic interactions, so static electricity kind of thing. Many surfaces in water will have some charge. We have many ions in water typically, allowing that charge to be felt in solution. And so what happens is the electrostatic interactions, if something has a charge, will be the long-range stiff arm. It'll say, hey, if you're negatively charged, I'm negatively charged, we're not going to get too near each other because I'm going to repel from that. And that happens because if we have some negative charge, and this is typical, there's some surface chemistry reasons why negative tends to be the charge on a surface. We won't get much into that. I can tell you more if you're interested, but it's kind of chemistry reasons there. So if we have negative charges on the surface, then the next thing that will occur is that will attract cations, so things like sodium or calcium, to arrange nearby. So these will be just floating in solution, but in general, they will come nearby. Sometimes you'll have a 2+ somewhere, and that'll satisfy more. And you can see that as just natural ions in solution, you can think of sodium chloride, NaCl. We'll do this. So sodium and chloride essentially is what you get if you put table salt, sodium chloride, into water, right? And so almost all water, has a fair amount of ions, especially any natural water that we might be treating, is going to have some presence of ions, okay? So what happens here is we get a nice layer at the surface, and actually I'm going to change this drawing a little bit, and I'm going to put circles around the ions, and I'm going to erase the circles to say the surface itself has some charge. And what we'll end up getting is, with this surface charge of this negative surface charge, we will get some positive ions making a layer, and then sort of a loose layer of negative ions a little further out. We'll go back to... And it won't be perfect. It'll be a little messy and a little bit random. There will be diffusion still. But in general, you end up getting a net double layer, an electrical double layer, where both particles kind of have a stiff arm out saying, hey, you're not getting any closer to me because as soon as you do, I'm pushing you away with my electrostatic charge. You had a question? We haven't talked about that yet. So these are just two particles, and I'm explaining how they stay apart so then we can understand how to bring them together. Actually, that's a pretty good general rule of thumb. If you get any clay particle or almost any particle, usually it'll have a negative surface charge in water. There are a few exceptions, but almost always. Yeah. So the negative charge keeps them apart? Yeah, so the electrostatic repulsion, when you have two particles of like charge, if they're different charges, they're just going to stick together. And this is typical. So these will be a repulsive force keeping them apart at pretty long range. In fact, I'll draw this a little better to say that kind of range. Yeah, good questions. And did we have another question? Okay. All right, so with that, we have some understanding now of what can push them apart. But now if they had no charge and they happen to meet, it turns out they would actually very likely stick together because there are attractive forces as well. So we have what are called the van der Waals forces, and there are many forces within this class, but essentially they are all the other stuff that makes something sticky. So if you've ever seen a gecko walk on a clean glass surface, or even taken a I don't know, a piece of plastic with a little bit of water on it, put it on something that like a very clean surface, and it sticks, and that suction effect. Well, what's happening is you have short-range sticky forces, and we just call them van der Waals, and they include things like your electron orbitals. If they get close enough, they have some attraction. It's not charged, just the orbitals themselves overlapping. You have magnetism. You have a host of atomic forces when you get close enough. The trouble is these are very short range. So we're talking, these start dominating at something like 5 nanometers apart, whereas the electrostatic might be pushing out 20 to 30 nanometers potentially. So the trick is, if we can reduce the stiff arm distance, if a particle can, maybe we'll use a stupid analogy and say, put on some deodorant so that it's not so gross to be near that particle for the other particle. They get close enough, and maybe they hug. And they like to hang out then, and then they're forming one larger particle. So what we want to do then is find some way to reduce that electrostatic interaction. This is called the electrical double layer, when we have kind of a double layer of ions next to a particle, and this is really what stabilizes the particle and prevents it from aggregating and then falling out. Okay, does that make some sense? Okay, so then we actually need a tiny bit more chemistry that we'll talk about just to understand how do we quantify how much charge is in the water, because it turns out if you add a lot more ions, then this distance will shrink. Because as I drew it here, yeah, there's a fair amount of ions, but if we overload it with ions, then the distance between each ion, because each of these that are kind of hanging out in solution, they're just going to be more dense, so that will automatically shrink it. And if they are higher charged, so we have this double charge here, if they're more highly charged, they're occupying more charged space at the surface and also serve to shrink this effect. And they make it all more dense. So if we add a bunch of ions, there's no longer what we call the osmotic pressure. Osmosis is trying to have a nice clean gradient of charges throughout solution. So if you had lots of charge and then some dilute water, some pure water somewhere else, they're going to want to cross some barrier and equilibrate the charge, right? It would want to do this. So charges want to spread out throughout a solution. That's the osmosis. If you have some membrane, we can talk about reverse osmosis or osmotic pressure, things like that. Water wants to move if it needs to, or ions will move to spread out and have a nice distribution. Okay, so if that's true and we add a bunch of salt to our condition, the repulsive effects here will shrink, because normally the osmosis kind of pulls them apart a little bit and makes it a long-range effect. Sorry, I hope that makes some sense. I don't feel like I explained that very well. I have some more diagrams that hopefully it'll make a little more sense. So the double layer effect, if we imagine some negative charge on the surface here, then we can say the first layer of ions will end up pretty much making a nice layer there. All the cations like to be there next to the surface. then we get a pretty good layer, and then a next set of anions. So we'd have anions and cations, just positive and negative. And then out further in solution, we just have the bulk liquid, okay? And then the distance here is what we care about. This is again, the electrical double layer. So that's just someone else drew it for us. And you can imagine if we have very few ions out here, it kind of pulls everything and stretches it out a little further. You still get a double layer effect. It's just stretched out further into solution because of the osmotic pressure is pulling these ions a little further, almost like pulling a spring. Okay, so what can we do with that? Well, let's take a look at what happens when we add salt. It's 3 different figures. The numbers are too small, so I'm just going to talk to you about what's happening in them. And I'm actually going to start with this one here, this figure. This is showing us relative turbidity. Now, turbidity is a fancy term for how much light is being scattered by particles in the water. So this is the number of particles that are there. Okay? So kind of like a concentration of particles. So, and it's a percentage. So at 100% up here, all the particles are in solution. They're all hanging out, stiff-arming each other, happily floating along. We would call that stabilized. Okay, they are stabilized with respect to each other. They're not meeting, hugging, and aggregating, right? And then sedimenting. So this is up here at 100%. We're saying stable particles, meaning no aggregation. Then we are dosing some coagulant, and we're trying 3 different ones here. We're going to try something that has aluminum, Al3+, here, something with calcium, Ca2+, and then sodium, Na+. We could imagine it might simply be something like aluminum chloride, AlCl3, calcium chloride, CaCl2, and sodium chloride. And the reason I'm writing it that way is because then we just have this chloride will just be a -1. And the point that we're looking at here is what's the impact of the charge and how big the charge is, or how dense the charge is. Because remember, I was showing you if we had a 3+ charge, that's a lot of charge in a little space. It's high charge density. It's going to shrink our double layer better than a 1+. And so just by saying we're just going to ignore the anions, the minus charge, can also be important, but just for the sake of, if we hold everything else constant and look at what happens if we change the cation, this graph is pretty interesting. So at some point, when we are adding our coagulant, we're dosing more and more of it, so this is milligrams per liter. At some point, all of the particles suddenly fall out of solution. The turbidity decreases. We went from as much turbidity as we had at the start to pretty much 0%, meaning all the particles stuck together and then sedimented. Okay, so that's what's happening in this experiment. Suddenly, we have sedimentation. So that happens for the aluminum at about 10 milligrams per liter. Now for the calcium, this is a log plot. So then for the calcium, we continue on until about 100 milligrams per liter, then everything settles. And for sodium, we go all the way up to 10 grams per liter, 10,000 milligrams per liter, until that causes sedimentation. So adding the salt, adding the more charge, makes that impact. It compresses the double layer. It causes particles to get close enough so that the van der Waals forces take over. They meet each other, they actually have a handshake, and they settle out. So at that point, we see that just simply adding salt can do the job. But have any of you tried drinking salt water? Anybody know the concentration of salt in seawater by any chance? That could be right. How about in milligrams per liter or in grams per liter? Anybody know? 60 what? Grams per liter? 60 milligrams per liter, that's a little low. But I appreciate the guess. And anybody take an oceanography or anything coastal related? Anybody ever do any recreation in Lake Pontchartrain? So Lake Pontchartrain, it varies a little depending on where you are, but it's about 5 grams per liter of salinity. It's approximately what we call sodium chloride. If you go off to Grand Isle, you'll get saltier water, right? If you go all the way out open ocean, you'll get pretty salty water. It turns out seawater on average is something like 25 to 30 grams per liter of salt. So if we're thinking about water treatment, this value here, 10 grams per liter, is approximately twice as salty as Lake Pontchartrain. Now, is Lake Pontchartrain, does it have a lot of particles in it, you think? Okay. A lot of you are like, oh, yeah, I've seen it. It's kind of muddy. Any of you ever been out way into the open ocean away from any estuary system or seen photos of like some beach that's, you know, remote and crystal clear water? Well, it turns out that one way to get crystal clear water is to add a lot of salt and give it enough time for any particles to settle out, right? And so you can expect that in estuary systems that are carrying a lot of sediment from rivers that were stable particles, at some point they're going to destabilize and start settling out. It's going to take some time. So as the Mississippi with so much sediment comes out, it's going to take a little time and area and space for that sedimentation to occur, and for the salt to mix and everything. But once it mixes and once it hits some certain threshold of salinity and of these ions, and seawater will also have some aluminum and things like that. So it'll be a little different than this chart exactly, but you can imagine at some point you're going to have added coagulant by mixing with the seawater, okay? And then you'll have sedimentation, and we get a delta, all the sediment dropping out. Then, of course, if there's sediment on the seafloor instead of sand, anytime there's any wave action, it's going to kick back up. And even if Lake Pontchartrain was, you know, perhaps salty enough to cause a lot of it to settle out, it's shallow and muddy. So anytime wind comes through, it's going to stir up a lot of that back into solution. So you can kind of start thinking about our natural systems by this, and you also see that 10,000 milligrams per liter is way too much salt to be adding to something we want to drink. Salt in general, table salt, is kind of hard to remove from water, so that's especially the case. We're not going to use sodium chloride as our coagulant, even if we technically could. Okay, so the graphs on the left are just going to show us a little bit about the distance of this double layer stiff arm thing, okay? So the one at the top, we're looking at, this is called potential. This is a measured charge, essentially. And down here, we've got distance in nanometers. So it's the strength of the repulsion for some distance, and then we check it with different concentrations of sodium chloride at the top here. So we've got 60 milligrams per liter for this line. And we see that, you know, maybe if it takes, the units here are millivolts, maybe it takes 20 millivolts worth of charge to have repulsion, something like that. Then we can see how far into solution does that occur. Well, that is about 20 nanometers. So we've got a 20 nanometer long stiff arm, one particle to the next, and that's plenty to keep them stable and apart. If we add 600 milligrams per liter, well, now we are arriving right here. And we're looking at 6 or 7 nanometers out into solution. It still turns out it's sufficient, and we can see that from this plot over here, right? It took quite a lot. Then if we add 6,000, so 6 grams per liter. Okay, then we're looking at just a few nanometers, like 3 or 4 nanometers. Still might be enough, but we're getting very close. So we can see what impact this is having on this distance, right? This distance at which the electrical double layer extends is really important. Okay, then the last one on the bottom here is going from a +1 to a +2 to a +3 or a 3+, however you want to say that. So just like the first graph we looked at, and then again, how far is it going given some, I don't remember the exact amount. This was probably 60 milligrams per liter of a +1, +2, or +3. So you can see the increasing the charge makes a big difference. So when we think about what kind of coagulant we want to use, well, if we can find something like that's as effective as aluminum, but is also something we don't mind adding to water, or we could easily remove from water, that would be ideal, right? Because we don't need much of it, and perhaps we can make use of the chemistry and take it back out. So it turns out that aluminum sulfate, is a really great option. All right, so here's the little bit of chemistry, which is just actually a very small algebraic formula. It's really not a big deal, but I wanted to add this one. You have this equation on your equation sheet. This is for ionic strength. It's a way we can get concentration of charge in solution. Okay, some of you probably seen this before. The equation is our ionic strength, I, or maybe sometimes you'll see it IS, is equal to 1/2 times the sum of all the concentrations of the charged species times each one of their charges squared. So this would look like I equals 1/2 times x to the charge of x squared, plus y, the concentration of y times its charge, whatever it is, squared, and so on. It's very simple. The only thing you need to know is that you have to find this in molar units because we're counting the number of charges, right? So we need molar units, and we just need to know something about their charge. So for sodium chloride, sodium is +1, +1 squared is 1. For chloride, it's a -1 charge, -1 squared is 1. Okay, so it becomes very simple. In fact, if we did the ionic strength of 1 molar of sodium chloride, turns out we have a mole of each. Each of them are times its charge squared, which is 1. We'd have 1 + 1, and half of that is 1. Okay, so the ionic strength of 1 molar of sodium chloride is 1. Very simple. Gets a tiny bit more complicated, but not too much. So let's do this example problem. I'll get the molecular weights here for you in a moment. But let's take the moment to practice your chemistry and solve for what if we have 100 milligrams per liter of magnesium chloride, find the concentration of each, magnesium and chloride, and the ionic strength. And remember, or take note that what we're going to do is we're going to dissolve this magnesium chloride. It will all dissolve, and we'll get magnesium and 2 chlorides per molecule dissolved. Okay, so I will find your atomic weights here. In fact, what I'm going to do is I'm just going to edit the slides real quick so we have them on there permanently. I'll give you this to look at. So I'm just going to continue solving it, so feel free to continue working on it. I'll walk you through it in a second. All right. Did you guys get an answer? So I'm actually not 100% per mole. So if we take our 0.1 gram per liter, divide that by the molecular weight, 95.2, we should get 0.00105 moles per liter of magnesium chloride. For every 1 mole of magnesium chloride, we get 2 chlorides and 1 magnesium. So then we can get our concentration for every 1 mole. We can look at it with stoichiometry, right? 1 here, and 2 here. So that's what we can point to and say magnesium then is exactly the same concentration as the concentration we calculated for magnesium chloride, 0.00105, and chloride is just going to be 2 times that. So it should be 0.00210, if I did that math correct. Then for the ionic strength, it's going to be 1/2 times chloride concentration times -1 squared. What you'll notice is that -1 just becomes, since we're squaring it, a negative times a negative is a positive. So the squaring it kind of just gets rid of the value, or it's like taking the absolute value of it in that sense. Then we're going to have the magnesium with a +2 charge, squared that. So it'll be 1/2 times the chloride concentration plus 4 times the magnesium concentration. So if I did that in the calculator correctly, and you can correct me if I'm wrong here, that should be 0.00263. 315? Okay. I don't trust the calculator app or myself with it. I almost pulled out Excel, but I was like, I should be able to do this, right? You said, okay, so 315? All right. And the units here are a little funny. It's almost like charge per volume, but it's not exactly. So it's kind of molar units of charge, but we're not going to bother too much with getting into the details with that. So if you describe it as molar units, I'm fine with that. If you leave no units for this one, I'm fine with that. This is a quantification that we're doing that is describing the amount of charge per volume. Okay, it's called the ionic strength. So here's one that will make it a slight bit more complicated for you. And I'll go ahead and add the sodium is approximately, should be 22, right? Oops. Is it 23 or 22? 23. So take sodium to be 23 grams per mole. It's just a hair under that if we include all the isotopes, and this problem will actually just have you do the same thing except test your chemistry a tiny bit. Because when you calculate the concentrations, you have to recognize what goes into a given concentration. So I'm going to let you have a couple minutes, but I'll go ahead and set up the stage here. And probably one thing you can start with is write out what should your ionic strength equation look like. And you're going to need, again, to find the different concentrations. All right, so I'm going to give you another minute to finish out the calculations, but hopefully what you notice or perhaps have stumbled upon is the fact that you have two different sources of chloride. You have magnesium and sodium chloride. So magnesium chloride and sodium chloride, both contributing to the chloride concentration, and you would be making a mistake if you put two different chloride concentrations in your ionic strength formula. So if you were thinking to calculate it separately, you're making a mistake because you only have one concentration of chloride ions in solution, even if you have multiple sources of them. Okay, so it's just a little chemistry refresher in case that I've seen that mistake before, so I wanted to call your attention to that here. You should be able to calculate the total chloride concentration, given the stuff that we dissolved in here, as one parameter. Okay, it sounds obvious when I say it that way, but I know that that's a common mistake. Okay, so our magnesium concentration should come out to be half of what we did in the last problem. That would be a little simple. Could have seen that. So that should be 5.25 times 10 to the minus 4. Our sodium is going to be exactly the same as the sodium chloride concentration that we added, so to speak. That should come out to be 8.55 times 10 to the minus 4. And then our chloride is going to be essentially just the amount that we added from this guy plus the amount we added by adding magnesium chloride. So that should be 1 times this concentration plus 2 times this concentration. Okay? So we're just really adding it up based on where it came from. So it'll be 1 times this 8.55 plus 2 times this 5.25. The amount here is 1.91 times 10 to the minus third moles per liter. And when we put all that into our equation, our ionic strength should be 0.00243. Yeah, and this time I definitely I used cheat codes and used Excel, right? So I'm a little more confident using Excel. But definitely always appreciate the double checks there. Okay, so that would be the answer here. So a tiny bit more chemistry review and one little new chemistry concept. As you see, you didn't learn any new chemistry really. It's just another formula that you can use, putting to practice a tiny bit of chemistry. So this will tell us how much charge we have so we can know whether or not we have enough charge to cause destabilization. That's why we might need it. Okay, so you can imagine all of this stuff about the grams per liter, how much does it take to destabilize the particles? we could also report that as some ionic strength that captures all of that in one place. Okay? Okay, so that's most of what I wanted to say about coagulation. I'll add just a little bit here to say often we will use aluminum sulfate, which is so Al2SO4 And if you look at this, this is going to give us 2 aluminums, which are 3+. Sorry. So the 3+ charge is huge, and then it'll give us 3 sulfates, which is SO4 Also a large charge there. So if we use alum, or aluminum sulfate, as a coagulant, you can see every gram that we add, we're adding a lot of charge. And not only that, so we don't have to add much, and not only that, it's actually quite easy to remove aluminum back from solution under normal conditions just by a little pH adjustment, and it will start precipitating a solid, and the sulfate doesn't bother us. It's a very low concentration anyway, and so we end up with a system where we can add a little bit of aluminum sulfate, remove the aluminum back out, and we've caused a destabilization and even started precipitating some solids that help with that particle gathering process. Yeah?
I know that we added the chlorines together to get the answer. Would there ever be a situation where we have to subtract?
I don't see a way where you'd have to subtract anything directly like that. It's very rare that you like yoink out a particular chemical. And maybe if you precipitated something, but I'm not planning to put you through that kind of stuff. But the overall point is a concentration is the concentration throughout, and you might add, a little bit from this reagent and a little bit from that other chemical.
So like those 2 concentrations is the 1 concentration for the whole, like those together are the 1 concentration.
Yeah. So you could maybe it would help to think about, let's say, baking a cake. Maybe your cake mix has a bit of sugar in it, and you add a bit of granulated white sugar, you add a little bit of powdered sugar and some brown sugar or something, maybe cookies, let's say. No, that's probably not what you're doing with cake. So if you do something like that, you can then find your total sugar concentration, but you added it in several different forms, right? And that's the point is what we're doing here is on the charge basis. It doesn't really matter where it came from as long as we're tracking how much total we have. Yeah, good questions. Okay, so aluminum sulfate, alum stuff, that's what we often use. Sometimes we will also use polymers, which you can think of as long molecules that are kind of like little bridges that will reach from one particle to the other and grab a hold of it. So we might have, I'm just going to do a little separate thing here. So alum is one thing, and then polymers that might have a positive charge on one side, some branchy thing, and then a negative side somewhere else, so they could bridge across particles, or maybe a positive charge on each side and grab 2 negative particles. So we have lots of different clever ways of adding something in small amounts that will come right back out with the particles we sediment to improve sedimentation. What I wanted to focus on here was kind of the basic using ionic strength to destabilize particles in order to induce flocculation. Okay, so that brings us to how do the particles meet, how do they mix, and how do we model that mathematically? So I'm going to go over the premise of that, which will bring us all the way back to our mass balances that we've started the class with. And next time we'll kind of work through some problems with that, and then probably have time to introduce the type of filtration that we would follow this with, although the granular filtration will be on the second exam, not the first exam. So I will tell you during class, like, okay, you can ignore this for now. We'll make a very distinct cut, and I'm just going to introduce the topic because I think we're actually further ahead than I thought I was. Okay, so flocculation, we are going to form these flocks. These are going to be larger particles than the individual particles. This is a nice little diagram. Bright green flocks here forming. And you can see there's still particulate matter, but they're probably kind of loose things where you could stir it up again and separate them again, but they're starting to come together, coalesce, and then settle out. So what we need for that is first for them to be, the particles to be destabilized. So if you see in a problem, we're going to talk about particle stability. We will often see completely destabilized, or we can even with the math, as we'll see, we can do a partial destabilization. It'll just go into what is our rate constant for how quickly these particles are meeting and growing. Okay? So if we mix particles together and we have some destabilization, we're going to reduce the number of particles over time. Now, when I say that, what I'm referring to is it's not that we are destroying them, it's that when two particles meet, I'm saying that they're becoming one new particle. So therefore, by two particles meeting, we've not lost any mass, but we've reduced the number. Okay? So when I say we have 4 particles becoming one new particle, the N initial would be 4 per volume. And now we have N is 1 per volume. Okay, in this little diagram. So in that sense, we are reducing the number of particles. And it's not a perfect assumption, but if we're taking our assumption that our particles are all the same size and they're all spherical, and then they make some new particle that also happens to be somehow perfectly spherical, we can then have a good estimation of the change in their density, the change in their size, and therefore the change in the sedimentation rate when all this happens. And in fact, we're going to keep the density the same for these problems. It turns out it sounds like gross assumptions, like how could this ever be accurate? But it turns out it's actually fairly practical, and with a combination of some simple modeling plus some just field tests or empirical tests, like, okay, how fast is this working? We get a good feel for how fast, what kind of sedimentation do we get, and what do we need to do to achieve it. So flocculation then is reducing N over time. We're going to have gentle mixing to allow the particles to meet, but we don't want to rip them apart, right? You can imagine if you take your nice little flocks that you're gently mixing and then you shake it real hard, they're all going to break apart again. Kind of pointless. So we do rapid mixing in the coagulation dosing, mix it all up, and then we let it gently stir in a larger tank, slowly flowing through it, allowing them to meet, but not ripping them apart. That'll do this process where we're gathering larger particles. Then the question really becomes, what is K? What is our rate constant K? Anybody care to guess what order of a reaction this is going to be? And why is that?
I guess there's more like exponential process that can happen with them just coming together, I guess.
So no exponential process of them coming together, so not second order, is kind of what you're saying, right? So how do we typically describe a reaction order? This time, we're going to have a decay reaction here because the particles are sticking together. We're reducing the number, so that we're decaying the number, even though we're growing the particle size. So it'll be a negative. We'll have some K, and then the question is, what is the exponent here? So to your point, what dependency do you think it will have? Okay, so you think it's second order now. You're revising your thought. And why do you revise that?
Because you have like 4 particles, right, to become just 1 particle. So the amount of particles in solution can change by several magnitudes. So it would be like second order or exponential.
Okay. I can see where you're going with that. Anybody have some other thoughts?
It could be a first order reaction.
Maybe first order? Yeah, so definitely it's first or second. It's at least first because exactly right. It depends on how many are there. So the question then kind of becomes, and there's some good thought here about how many, to what extent does it depend on how many are there? And a lot of what we would call like in chemistry terms, bimolecular reactions, you have potentially dependence of the thing twice because it is two things meeting each other. But I'm going to just go ahead and short circuit this and say, well, this is a first order reaction. So your initial intuition was correct. It's, maybe we can look at it as multiple pieces meeting at the same time, but it's more likely that we'll just do one interaction at a time. And so for each reaction of two particles meeting, probably the best way to describe this will be a first order. But excellent thoughts there. This will be what our reaction rate equation looks like. And then what I want to get into is what goes into this K, and we'll have a fancy formula for that. So you'll have a formula on the equation sheet for this K. This will be specific to our flocculation problems. Okay, so one of your tasks navigating this course is to understand, okay, hey, here's a formula on the formula sheet. I know we've talked about it, but what are the parameters there? What scenario is this useful for? That's something that you'll need to know. Okay, so it turns out that K will depend on a few things. K will depend on how fast we're mixing. And we were just talking a moment ago about, can the particles even meet each other? If there are two particles in a swimming pool, they're probably not going to meet, not very often, right? And how fast you stir that will dictate how often particles will meet. So that's the first topic that I want to talk about, is the mixing intensity. So K will depend on, and in this case, this slide, we're talking about mixing. So a mixing intensity value, perhaps a good way to describe this is from physics. If we imagine some surface with water moving across it, or maybe this is a surface that's moving through water, like a little spinning propeller to stir your water. If this is moving through water and you have distance away from your surface and some velocity of water passing across your surface, it turns out there's going to be some drag forces, and your velocity term will grow as you go further away from your surface. At least for some transition zone, you will have a gradient where, because of the forces of drag, the differential between water at that surface and water further out will be changing. And so you'll end up with some gradient here that's dV dy. And that slope is our mixing intensity. And if we look at this, that will be a change in velocity. So change in, let's say, meters per second divided by meters. So this will give us units of 1 over time, or time to the minus 1, seconds to the minus 1. So our mixing intensity can be described in this way by saying, okay, we've got a paddle wheel or something flowing through. How steep is this gradient? If it's moving very slowly, the water right next, let's say you're pushing your hand through water when you're swimming, right? You can sense that if you're moving it really quickly, there's a lot of drag, and you can sense there's a big difference between how fast the water is moving compared to your surface, your hand. Or if you're moving slowly and you're even pushing some of the water along, there's not a big difference, right? It's a small gradient. So you can feel this mixing intensity if you just take a spoon in water or whatever. And that's a nice way to describe it. It's the steepness of that slope is a way to describe our mixing intensity, and it's going to be in per time units. We have a formula for that. Mixing intensity we're going to call G, and this formula is the square root of the power that we're putting into it divided by the volume of this basin, whatever we're stirring, times the, and this is, I guess, the power divided by also the dynamic viscosity. Question? It doesn't even matter. We're not going to go that far into it. But yes, I guess we probably would. That probably would happen. I'm showing you this just to show you how what it means physically. You can forget about it, actually. As long as you know what G is and can use it, we're fine. I just wanted to show you what it physically is, and you can go to your fluid dynamics class and care more about the actual equations here and what to do about it. What I want you to know is, what is it, and why does it mean this? And if we take a look at this G and this equation, another equation for your sheet. It's a very good question, by the way. Don't mean to dismiss the question. I'm not going there with you guys, and I just want you to know that you don't have to worry about that. If you tried to stir a container of peanut butter, the kind that's like doesn't have all the vegetable oils in it added, it's just the peanuts, it tends to separate. So you have to stir it. It's very viscous. So you have to put a lot of power into it. You risk splashing all the peanut oil everywhere. But if you're trying to stir it, it takes a lot of power, even though it's a small little volume. If you try to stir a big jug of it, it's going to be even more, right? You can imagine that power required is going to affect your mixing intensity. If you really put a lot of power into it, you're getting better mixing. That example is showing you the importance of the viscosity. You could also consider how effective is it in some volume. So you can imagine putting a little propeller in a swimming pool, even if it's putting a lot of power in, it's not making a big difference. Okay, you need a lot of power for that big volume. Okay, so I'm going to leave off there. We'll come back and start here next time.